In section 2.1, we're going to look at some qualitative analysis for some differential equations. So some of the fundamental questions we have, we've already kind of covered in the last chapter this, existence and uniqueness of solutions for certain differential equations. One of the other things that we might want to know is what is kind of the end behavior, how does a solution behave as x approaches infinity? And this is something that we can actually determine without necessarily having to solve the differential equation, especially when f depends solely on the y variable. And this is going to bring us to the concept of what's called a slope field. First of all, recall from calculus that the derivative dy dx of a differentiable function y equals to y of x, so y is a function of x, gives the slope of the tangent lines at the points on its graph. Okay. Let's suppose that we have dy dx is equal to some function of x and y. Then what we're going to see is that if this derivative exists, then it's going to be differentiable on its interval I of definition. That means that it must also be continuous on I. Thus, the corresponding solution curve on I must have no breaks and must also possess a tangent line at each point x comma y of x. This is one of the big implications from calculus, is that when things are differentiable, that implies that they are continuous. The function f in the normal form above 1 is called the slope function or the rate of change of the function. So here we actually have an expression for the slope at each point x comma y, and it's given by the function f of xy. And we know from this that the value of the slope is given by this function. Now let's suppose that we pick a point, and this could be any point in the xy plane of the region. We can actually form a segment of the slope of the solution curve at that point x comma y. This little slice of the slope is going to be what's referred to as a lineal element. For example, let's look at the differential equation dy dx equals 0.2x times y. So here's our dy dx, and it's this thing on the right hand side. This is our function f of xy. It's 0.2xy. So if I pick a point, let's just work with the point 2 comma 3. If we plug that into this function f of xy, that would tell us that the slope of the derivative, so dy dx, the slope of that solution, is going to have the value 1.2 at 2 comma 3. So we can come over here. Let's go 2, go up 3. Here's this point. We know that we can draw a little, what we call lineal element. It's going to be a segment of a line, very small in nature, that has a slope of 1.2. And what that tells us is that when the solution curve y equals y of x passes through that point, it's going to have a slope of 1.2. We can continue to kind of within that rectangle bootstrap and create a lot more of these lineal elements, and that will kind of tell us in which the direction some of the behaviors would be of the solution curve y equals to f of x. The collection of all of these line elements or these lineal elements is what we're going to call a direction field or a slope field for the differential equation dy dx equals f of x comma y. Visually, this direction field will suggest the appearance or shape of a family of solution curves of the differential equation, and then consequently it may be possible to see at a glance certain qualitative aspects of the solution without actually being able to solve the equation outright. One of the things, and I'm going to post this in the YouTube comments and probably also on the home screen, is that we can actually plot these using technology. In my opinion, this is one of these things where I might ask you to do one by hand, just one time ever. But calculators and computers can do these much better than what we can. There's a nice link in GeoGebra, which is a great online graphing applet, where you can actually put in that function f of xy. Here for this example it was 0.2xy, and then we can plot it, and this will actually kind of show you what the slope field looks like. By hand, we did the one at 2, 3, which would be this little lineal element right here. That line has a slope of 1.2. And you can kind of see what it looks like if you were to trace along these points, making sure that your tangent at each point, that would show us some solution curves. Okay. For example, if I had the initial condition that the point had to pass through 2, -1, then this would be what our solution curve would look like. I can add another solution. If we had the initial point -2.64, 0.92, we would get this solution curve. Again, at each point, its slope is given by that function f of x, y, which for this first example was 0.2 xy. Here's another one. This would be the direction field or the slope field for dy dx equals the sine of x plus y over a subset of the real plane. And you can see really kind of like how the three solution curves show the color, how they follow the direction that's posted there. In the first example, we're going to kind of go back and revisit dy dx equals 0.2 xy, the one that we just saw. You can see really quickly what's happening to the slopes. So as x and y both increase, this quantity is going to increase. So x and y both increases, this increases, and you can see that as we go further out in the first quadrant, that these slopes are going to get higher and higher and higher. And what that's going to tell us is that our solution will, in fact, in this case, it'll approach positive infinity. If you had an initial point that was in the upper half plane, the solution would approach positive infinity as x approaches positive infinity. Whereas down here, if we had an initial point in the lower half plane, then as x approaches positive infinity, we see that these solution curves would get steeper and steeper and steeper negatively, and therefore it would approach negative infinity. And if you think about sines, that makes a lot of sense because let's go back to that function. It was 0.2x times y. If you're in quadrant 4, x is positive but y is negative, so that gives us a negative value for the slope, and the magnitude increases as we go further out to the right. So a lot of this analysis that we can kind of just glisten off of by just plotting it, and I'll put that link to the GeoGebra .org app, and it allows us to see up to 4 solution curves to see what it would look like. Let's take a look at another one. In example 2, they ask us to use a direction field to sketch an approximate solution curve for the initial value problem. Dy dx equals the sine of y, and we want to look at, for the initial solution, y of 0 equals -3 halves. So let's come over here. So our f of xy in this case is simply going to be the sine of y. So this is what we would get, and we wanted to look for the solution that passes through 0, -3 halves. If we were passing through 0, -3 halves, that would put us here, and so you can kind of see like what the solution curve would do. So our tangent here, follow through, and then it's going to kind of level out and go something like this. It would be very kind of similar to this one here, but just translated down a little bit. This one we can see that as x approaches positive infinity, this thing only depends upon y, it looks like it's going to flatten out, and we can actually go out a little further if you'd like. looks like this. So here's our little direction field. Again, we were able to graph it. Picking this as our initial point, that would generate the solution curve like this. One of the things we would like to do is interpret the increasing and decreasing nature of the slopes. So the interpretation of dy dx is a function that gives the slope plays a key role in the construction of a direction field. Another telling property of the first derivative will be used next. That is, if dy dx is greater than 0, for all x in the interval I, then the function is increasing on the interval I. And then conversely, of course, if the derivative is negative, we recall that that means that the function is a decreasing function. The next thing we're going to look at within this section beyond slope fields is autonomous first order ODEs. What we mean by a first order autonomous ODE is simply it's a differential equation where instead of having a function of x and y on the right hand side, we just have stuff that involves the y variable. So dy dx is simply going to be equal to a function of y. So it's an ordinary differential equation in which the independent variable does not explicitly appear. It's said to be autonomous. Okay, don't forget, it's actually there. Our solution curve, when we're thinking of y is a function of x. On the left hand side, that's dy dx. So y does depend upon x, yet our differential equation doesn't explicitly have the independent variable in it. That's what we mean by an autonomous first order ODE. Again, first order because we're just looking at the first derivative right now. An example of a first order autonomous ODE would be dy dx equals 1 plus y squared. Again, because with dy dx by itself, we see that the right hand side only involves the y variable. Whereas the one we just looked at in example 1 of this section, dy dx equals 0.2 xy, this would be a non-autonomous ODE because you can see the explicit dependence on the independent variable x as a part of it. Many differential equations encountered in applications or equations that are models of physical laws that do not change over time are autonomous. If we simply go back through our section on modeling, so whether we're doing population dynamics like the first two, radioactive decay perhaps for this one, Newton's law of cooling, or that tank mixing problem we were looking at a little bit ago, these would all be examples of autonomous first order differential equations. Intuitively, we're thinking of all of these quantities as being functions of time, but on the right hand side it only involves the ax, t, and a function. You don't see any explicit dependence on time anywhere in that differential equation.